Okay, I guess we can get started. So hello everyone, I hope you can hear me properly. My name is Rohan Kadekudi and I'm from UT Austin. And I'm happy to introduce you again to this initiative, which is a joint webinar series between BigHPC Project and the UT Austin Portugal Program. I wish to thank all of you for participating in this session. And in this webinar, we'll welcome Julio Silva from Wavecom, who will talk about monitoring in BigHPC lessons learned. So Julio graduated from the University of Aveiro as a Master's in Science in Electronics and Telecommunications Engineering in 2020. And being a data enthusiast, he joined Wavecom's Research and Development Department in 2021 to work in BigHPC monitoring activity as a data analyst. In the last year, he has been mostly working in data-related tasks for the BigHPC monitoring prototype. His main focus has been the collection, processing, and analysis of all metrics related to monetization of jobs and compute nodes. Currently, he's focused on integration tasks with other activities. In addition to BigHPC, he's working on other Wavecom projects related to data analysis and machine learning. As mentioned before, my name is Rohan Kadekodi, and I will be the moderator of this session. I would like to inform you that you can and should interact during the presentation. To do so, you can use the chat to share your questions. During the presentation, there are no discussion moments, but at the end of the webinar, we'll provide some minutes to discuss all the questions and interact directly with Julio. I will be monitoring the chat activity regularly, ensuring that all the questions are dealt with by the speaker at the end. Now let us move on to the presentation. I kindly ask our first speaker, that is Julio, to share his screen in order to kick things off. The screen is yours. Please start.
Thank you for the introduction, Juan. I'm going to share my screen now. Can you confirm that the screen is being shared?
Yes, we can view the screen.
Okay, so let's start. Hello, everyone. Today we are going to talk about monitoring in BigHPC. As it is stated in the title of the webinar, we are going to focus on some of the lessons we learned since we started the BigHPC project. So before we start, I want to give you a general overview of what we are going to talk about. First, we have a small introduction to what we define as monitoring. We then talk about the faced HPC challenges by the monitoring. And next, we have some limitations and requirements for the monitoring component in the BigHPC project. Afterwards, we are going to introduce our proposal solution for the monitoring of jobs in HPCs, where we go a bit in depth about the prototypes developed for this project. After introducing the solution, we then explain some of the available functionalities of our architecture and the challenges we faced so far till we reach our current solution. We then talk a bit about the prototype collection times when the node is under stress by hundreds of workload processes. Finally, we have a prototype video demonstration to show you of our dashboards, and then we talk about the conclusions of the project so far. So, how can we define monitoring? We can first split it in different steps. We first have the extraction step, which is basically in order to monitor a system, we require metrics. Therefore, we have to have an extraction stage where we collect required metrics to monitor a given system. We then have a transform stage. In this stage, different transformations to the metrics might happen. In our case, we use this stage to convert our collected metrics in order to be compatible with our storage solution. Then we have an aggregation phase. In this stage, we have our metrics are pushed to a middle agent that buffers the data instead of directly pushing it to the database. On the fourth stage, we have storage. This is where the metrics are kept until they are deleted or they are queried from the database in order to be worked with. And finally, we have the most important stage for the sysadmins or users. Here we have dashboards, alarms, and analytics. They basically allow the user to better understand their job performance thanks to the metrics that are stored in the database that were extracted in the first stage. So some of the challenges we faced in HPCs are it's that the HPC scenarios amplify the problem because they have thousands of nodes. And we can extract metrics from hundreds of different system metrics from hundreds of different nodes, which generates a lot of information which can be irrelevant. So we should really only focus on necessary metrics to monitor the resources that we require. So having knowing this, that these are such complex systems, how can we give knowing that a user can require hundreds or even thousands of nodes for a single job, how can we, the monitoring, digest all of the collected metrics from all the different available resources for every single node associated to a single job in an easy to comprehend monitoring dashboard? So this is the real challenge we face. Some limitations and requirements we have regarding the BigHPC is that we can't pull any sort of data from compute nodes because of security reasons. Therefore, any monitoring solution based in pooling methods does not work in our scenario. Again, because of security reasons, root access is restricted in compute nodes, which limits our solution only to options that require no elevated permissions. And since Docker is not available in compute nodes, we also had to find another container solution to develop our monitoring probe for HPCs. Furthermore, the monitoring probe should have minimal impact on the compute node resources. This is obvious because jobs should be the ones using most of the resources available in the node. And it was also decided for the BigHPC project and all the partners that the database should be shared and should be SQL based. And finally, a requirement for the monitoring solution is that we should store data in the long term so that users can have a track record of how their jobs perform, and sysadmins can also have an history on how the nodes are behaving. So what's our proposed solution? In this slide, I want to provide you a general overview of all the components that are part of the monitoring solution. We'll talk a bit more in depth about each single component in the next few slides. However, this is the main takeaway. Actor is a monitoring probe and a metric transformer that runs inside a singularity environment inside the compute node. In an external machine, we have our monitoring architecture, which we call Monica, which is constituted by VM agent, PromScale, and Grafana. So basically, Actor starts by collecting metrics on the compute node. The metrics are transformed into Prometheus compatible storage and then pushed from the compute node into an external machine where the Dockerized Monica architecture is running. The metrics arrive at a port in the external machine that the VM agent is listening to. From here, the metrics are aggregated and written into PromScale if the remote write protocol connection is available. And finally, when the metrics arrive at the database, they are then queried by Grafana in order to plot the necessary visualizations for the monitoring of job status. So, in short, Actor is responsible for everything that happens inside the compute node, such as metric extraction and transformation, and Monica is responsible for everything that happens outside the compute node, such as aggregation, storage, visualization, and data processing. These two models, when working in conjunction, allow for an in-depth monitoring of the state of multiple compute nodes in real time. So now let's talk about different components of our monitoring solution. First, we have Singularity. It is a container platform. It allows to create and run containers that package up pieces of software in a way that is portable and reproducible. You can build a container using Singularity on your laptop and run it on any largest of HPC clusters that support Singularity. You can also run it in local universities, company clusters, single server, in the cloud, a workstation, wherever you want. The container, the Singularity container is basically a single file, and you don't have to worry about how to install all the software you need on each different operating system. In the monitoring component for the BigHPC, we use the Singularity in order to convert a Docker image of Actor into a Singularity image capable of running in the compute nodes. Then we have Actor. Actor is the monitoring probe of the monitoring component. It is based in Python language, and it is supposed to be permanently running in the node, monitoring both the node and the jobs that are deployed into the node. Actor collects metrics from different compute node resources, such as CPU, memory, disk, network, processes, system utilization, lustre, GPU, and InfiniBand. After collecting metrics, they are transformed into Prometheus format using the Prometheus client API. And after transforming and collecting the metrics, after collecting and then transforming the metrics, they are then pushed into a port on the external machine where VM agent is listening to, as I previously mentioned in a few slides back. Now, Hector runs in the background of a compute node monitoring different resources. It can be configured to extract metrics at an higher rate by the sysadmins. The current default has been 20 seconds for testing purpose. And when jobs are deployed into the nodes, they usually create a number of different processes that generate different workloads, which can stress a range of different resources. Some workloads might be more GPU intensive, others might be more CPU intensive, and others might be more disk intensive. Hector basically monitors the impact of that job and the respective processes and workloads that have on the compute node resources. And now I want to talk to you about Monica, which is basically a monitoring architecture in container. It is an architecture that encapsulates everything related to data processing, storage, and visualization. It runs outside of the compute node and it is containerized. It's basically a Docker architecture. Our storage solution in this architecture is PostgreSQL with PromScale extension. We offer long-term storage by using downsampling techniques. For our visualization of metrics, we use Grafana, and the available query language are PromKL and SQL. Now, for the aggregator, we have VM Agent, which is open source. It is created by Victoria Metrics. It can collect metrics from various sources and store them in a storage system compatible with Prometheus Remote Write Protocol, such as PromScale. It provides also buffering of data in case of connection failure, and in case that happens, when the connection is reestablished again, the data is unloaded to the database. It can be used as a metric push destination, which is excellent for us because it allows us to push data from the compute node to VM Agent. And VM Agent is also scalable. Furthermore, you can apply VM Agent in other scenarios. You can also configure it to pull from targets or use it with other and the VM Agent is also compatible with other protocols from other databases. Next, we have PromScale. PromScale is an horizontal, scalable, and operational mature platform for Prometheus data that offers the combined power of PromQL and SQL, enabling developers to ask any question, create any dashboard, and achieve greater visibility into their systems. PromScale is built on top of TimescaleDB, which is considered the leading relational database for time series data. PromScale also stores data in a dynamically auto-generated schema, highly optimized for Prometheus metrics that is the result of through benchmarking and community discussion. In particular, this schema decouples individual metrics, allowing for the collection of metrics with vastly different cardinalities and retention periods. At the same time, PromScale exposes simple, user-friendly views so that developers do not have to understand this optimized schema. And furthermore, it also offers us downsampling techniques that we require for the long-term storage. And final, on the end of our architecture, we have Grafana. Grafana is an open source interactive data visualization platform developed by Grafana Labs, which allows users to see their data via charts and graphs that are unified into one dashboard or multiple dashboards for easy interpretation and understanding. You can also query and set alerts on your information and metrics from wherever that information is stored, whether that's traditional serving environments, Kubernetes cluster, or various cloud services. You then are more easily able to analyze the data, identify trends and inconsistencies, and ultimately make your processes more efficient. Grafana dashboards also give a new level of meaning to data collected from various sources. Those dashboards can be then shared with other team members and other teams, allowing collaboration and more extensive exploration of the data and its implications. And it also allows to basically understand the relevant data and data relationships that you can use to find an incident or unexpected system behavior as quickly as possible. Grafana allows for seamless visualization and movement of data between teams and team members so that they can get to the root of a problem quickly and solve it. So now that I explained all of the components of our monitoring architecture, we can go back to this pipeline and attribute to a given stage a given component. For the extraction and transformation stage, we have the monitoring probe and the Prometheus client respectively, which consists on actor monitoring component. For the aggregated storage, dashboard alarms, and analytics stage, we have VM agent, PromScale, and Grafana respectively, which in turn form up the Monica monitoring architecture. And so as a final, more in-depth overview of the full structure of the proposed solution, we have the following diagram, which shows the full workflow of the monitoring. The monitoring starts in the compute node, actor collects metrics and pushes to VM agent after transforming the metrics. VM agent writes the metrics to the PromScale connector via the Prometheus remote write protocol, and then metrics can be queried from PromScale using either PromQL or SQL tools such as Grafana. Now, talking about some of the features of this architecture, we basically can start with PromQL, which is a Prometheus query language. It lets the user select and aggregate time series data in real time. The result of an expression can either be shown as a graph, viewed as tabular data consumed by external systems also. It's of simple syntax and open source. And as an example, you can have the following image that shows a Prometheus metric format. If we want, for example, to query a given job ID CPU usage percentage, we just need to define the correct job in the label value. So basically here we have the metric name, here is the label name, here is the label value, and here is the timestamp and the value for that metric. And I'm gonna now give a concrete example how this is how PromQL is powerful and allow us to make queries. In this slide, we provide, for example, if we want to get the aggregated average CPU usage for all processes named Python 3.10 for this job ID and for two specific nodes, we first write the name process CPU percent, which is the metric that stores the CPU usage for all the processes that are associated to jobs and nodes. And then we pass into the labels the respective information of the data we want to query, such as job ID, node ID, and process name. Finally, we aggregate and average them out by using the average operator. This concludes the query, and the result can be seen in the next slide. We basically obtain a time series result of the average CPU usage of the Python 3.10 process that ran in the selected nodes for the specified job. Now talking a bit about another feature, which is very important in this architecture, which is downsampling. Downsampling is the term used when reducing the rate of a signal. This means that you have fewer entries in your source data to take up less space on disk. The main reasons for downsampling are to reduce cost and increase performance. Querying downsampling data gets faster as the size of the data decreases. When you downsample data, the size of the data on the disk is reduced, but so is the resolution of the data. PromScale basically offer us two different downsampling methods. We have recording rules offered by Prometheus, and we have continuous aggregate offered by Timescale DB. So for recording rules, they are built on top of Prometheus recording rules capabilities. They are configured in a YAML file and specified in the PromScale configuration file. They are used to calculate frequently used or computational expensive queries before they are required. PromQL expression evaluates at a predefined frequency to generate a new metric series. The new metric series is then stored in PromScale and can be queried as any other metric. And this basically helps in the visualization of data over a long period of time because the number of samples is reduced. So here is an example of a recording rule. In short, what the recording rule does is creating a new metric series that aggregates the total sum of a rate of the metric API requests by customer by each day. We then can either query the new metric series with PromQL or SQL, as you can see on the two images on the right side. So for continuous aggregates, which is also a downsample technique offered by PromScale, we basically require a materialization hypertable to store the aggregated data in, a materialization engine to aggregate connect the data from the raw underlying table to the materialization table, an invalidation engine to determine when the data needs to be rematerialized due to inserts, updates, or deletes within the materialized data, a query engine to access the aggregated data, and it offers a very different feature from recording rules, which is backfilling. Continuous aggregates automatically downsample all data available, including past data. Recording rules do not include past data. They only include current and future data. So using continuous aggregate, we can basically downsample all the data, including the past data. In this example, we have an example for continuous aggregates. Here we use a metric called node memory mem3, and this shows how to create a continuous aggregate to derive some summary statistics, such as the minimum volume, max volume, average value for a given metric on an hourly basis. If using a continuous aggregate, in order to be able to query the new metric in PromQL, we have to register the metric view like it is in the image below. And then after doing this step, we can query the metric either in SQL or either in PromQL. Now, talking about going back on and talking about the actor monitoring probe, this is an example about the collection times when the node is under stress. In this example, we have a workload that continuously deploys more workload processes till it reaches a total of 252 processes that stress the CPU. We can see that collecting metrics from processes takes more time as more processes appear to be monitored. At the end, to monitor 252 processes, actor took around 7 seconds to monitor every single process and every relevant metric to that process. As the default monitoring period is 20 seconds, 7 seconds is a good scenario. Now I want to show you a small example of monitoring in large scale. Jobs can run in hundreds or even thousands of nodes. In this scenario, I present you a job that ran up to 392 nodes. This is basically the visualization in Grafana of all of those nodes being monitored at the same time. You cannot see all of the 392 nodes here because Grafana limits the number of nodes you can see at a given time. However, if this was an interactive visualization and it was in you were in Grafana, you could select any of those nodes to see the time series of the nodes being monitored. So the facet challenge we had so far, different HPC centers have different GPUs and different GPU drivers. Without Singularity, we will require to install the correct NVIDIA driver in the Docker file of Vector for every GPU and mount the respective libraries of the host into the container. However, through Singularity, we can do this automatically by using the NV command flag, which automatically binds the necessary libraries to access the GPU. Another challenge we face is that how can we extract the job ID we using Slurm commands, and basically we had to add the user Slurm and the environment path to the actor Docker file. This basically allows actor inside the Singularity environment to use Slurm commands inside the compute node. Without this, we couldn't know the job ID. And finally, the latest facet challenge was regarding Lustre. Basically, newer versions of Lustre have changed the metrics, the metrics from the directory proc-fs Lustre to syskernel debug, and proc-fs Lustre we can read from there. We have permissions to read. However, in syskernel debug, it requires root, so we couldn't get metrics from there, and we couldn't basically monitor the Lustre file system. However, TACC implemented a version of the lctl command with elevated permission that allows us to read from the Lustre files in the syskernel debug and output that output to a new directory where we can read from. And now I want to show you a demo of our dashboards. So basically here, what you can see is Grafana. And what you can first start seeing is that we have a menu for the jobs. And you can see multiple things. You can see the job status, total nodes, the start time, total run time, and you can select also where you can filter out the time range where the jobs might have been monitored. You can also basically put the columns in ascending or descending order, which is useful to find the most recent job or the most oldest job. Or you can also do that for the nodes and find the job with the most nodes associated to him. You can see also when a job is being currently monitored or it is already finished. And you can also filter for a given job. So here I will select this job and I will go to a dashboard that shows all the metrics of that specific job. In here, we basically have different rows that open mini dashboards with different visualizations for every single metric. So we have CPU, memory, network, and everything is related to that job and to the nodes associated to that job. So here we basically can see that we have time series data and the tabular data regarding the job. In the time series, we have average CPU usage across all the nodes. And you can see on the tables that we have multiple nodes and their average usage. However, we can select just a few nodes and this will update every visualization in real time. So for example, I selected here 3 nodes and all of those visualizations were updated in real time. We also have a histogram on the right side that allows us to see the distribution of values across all of the nodes and in the time range. And we also can go to a single, we can select single metrics on a given node and check just for that node a single time series. Here we have the memory. On the left side and in the color blue, we have the virtual memory, and on the right, we have the swap memory. These basically, all of these time series aggregate all data of all the nodes. And as I said before, we can order the columns by ascending or descending order. We can also zoom in on the time series and zoom out, as I will show you now. You can zoom in on the time series, and this updates everything on the dashboard. Every table, every graph, everything is updated when I click on the time range, or zoom in or zoom out. Here we have disk operations, more tables, more histograms. We can see the count, the read counts, write counts, the operations rate, read rate, write rate, and the time series of the total operations that happen in all of the nodes related to this job ID. So this is basically regarding disk bytes, and it's basically the written bytes and the read bytes. And this is regarding the GPUs. Here, basically, this job used 22 nodes, each has 4 GPUs. So this was basically 80 GPUs that were being monitored. And this time series shows us the average GPU usage across all nodes. You also have 3 different histograms here. And you can see that most of the GPUs were either on 30 degrees or in 76 degrees during most of the time. And as I did before, you can basically open a single node and see all the 4 GPUs and their utilization. And you can also do the same for the temperature. You can see the temperature of a single node and the 4 GPUs for that node. Now we have InfiniBand and InfiniBand errors. We can see that no errors were detected, and we also have InfiniBand data and packets that were monitored. Now we have the processes. These are all at the total processes that have happened in a time series graph. And you also have the total processes on the right side that have been monitored for that node during that entire time range. And here I'm going to select the CPU for a given node, and this will basically show the CPU usage of all processes that were monitored in that node. As you can see, this is not a very beautiful visualization, but it shows the CPU usage, the core usage across all processes that were monitored for this job, for this specific node. And this is the bytes that have been written in that node for all the processes. In here, what I do basically, I aggregate all the data from all the nodes into process name. I basically grab all the processes that are TF-CNN benchmark, Python 3, Saran, and it's aggregated by name. And so you can see clearly that the TF-CNN benchmark uses the most CPU usage on this table and the most memory. And also you can see here, for example, that in regarding bytes, Python 3 was the process that had more bytes across all nodes. Here we have lustre metrics, and this is basically the lustre operations. You can see basically every operation for every node and the rates of the operations. And here we have a rate histogram that shows us the values of the operation rate. You can see that we have very low rates at the beginning, but we also have operations that happen at 11K operations per second near the end of the histogram. So we have some very intensive speeds in some very specific times. And this is the bytes. Basically, we can see the bytes that were read and written in lustre, and the rates and the histograms. And this is basically the total operations. And in a time series, you can see basically the spikes that happen and how many operations happen at a given time. And in the tables, you can see the total operations and operations rate for every single lustre operation aggregated by all the compute nodes. And here we have a view of operations that is aggregated by the file system. So we have in yellow, we have Scratch, and that green, we have the home file system, and we have blue, the work, which does not appear because there was no operations happening there. And we can clearly see that for Scratch, the lustre node permission was the one that had the most operations happening. And finally, this is a view of bytes per file system. This aggregates all the data from all the nodes and aggregates to the file system. And basically, we can see that we have on the left side, we have the home file system. All the data related to the bytes for the home file system is on the left. On the middle is Scratch. And on the right side is the work file system. And this is everything regarding this demonstration. So as far as conclusions, so you just watched the prototype demo we have of our working monitoring prototype. I hope you enjoyed the video. And in order to solve the problem of finding compatible SQL databases, we implemented the PromScale storage solution. VM agent was a solution to solve the problem on how to extract metrics from compute nodes, since outside requests were not allowed. The monitoring probe has low overhead, however, it is capable of monitor hundreds of processes in hundreds of different compute nodes, as I shown before. Visualizations using PromQL are well integrated within Grafana, as you witnessed by the performance of the visualizations on the prototype demo video. And beyond all of these visualizations that I've shown you, metrics can either be further explored with data science techniques. And this is all. Thank you for your time and patience, and I look forward to answer any questions you have.
Thank you, Julio, for the great talk, and I think it was a great video.
Thank you.
So we can open up the session now for discussions of any questions anyone has. I don't see any questions on the Zoom chat yet. So please feel free to write any questions on the chat, or to also unmute yourself and ask directly to Julio. So until people have, sorry, go ahead.
Sorry to interrupt. Can I ask a question?
Sure.
Okay, thank you. Thank you, Julio, for the presentation. My question is the following. Given all this work that you have done, and after setting up all this pipeline and having everything working, what were the main challenges of doing this? So what have you learned, and can you help people that will work on stuff like this know in advance if they are doing monitoring pipeline like this one? So what are the important decisions or the key decisions on your perspective? And this is the first part of the question. The second part is what do you think are the big challenges that are still need to be solved? Thank you.
So I would say from all the work we've done so far, we have a lot. At least here on Wavecom, we have experience with Prometheus, but Prometheus is a pool-based method, and unfortunately, we could not use Prometheus in this scenario because you cannot monitor compute nodes from pooling techniques, because compute nodes are restricted only to push data. You cannot pull data from the compute nodes. Therefore, we had to explore other solutions for that problem, and eventually we also had to explore other databases. So, for example, we tried to use Prometheus Push Gateway, which basically kind of converts Prometheus to a push system, but it's not a very pretty solution, not very elegant, and it does not work great in a scenario so complex as this one. And another problem that we faced was basically, since the database had to be in SQL, we also tried Elasticsearch and Victoria Metrics that we have experienced also here in Wavecom. However, again, they have no SQL capabilities, so we have to find other solution, and eventually we stuck to PromScale, which basically allows us to have the best of the both worlds. And I believe that was a very big challenge at the beginning. Another challenge, I would say, it was, it was not really a challenge, because Singularity is actually relatively easy to work with, but when you don't have experience and it's the first time that you start working with it, it might seem a bit complex. However, after those two were after I learned how to work with those two technologies, I think it was okay. Now, regarding the things that we need to tackle that might be complex and we still are not yet sure how we'll solve, or on how things are going to be solved, is, for example, on how we can associate a user to a job ID in the BigHPC use case. That is something that we still have to work in integration and integrate with the monitoring also, because we want users to be able to only look at statistics of their jobs and not the jobs of other people. So I hope I tackled your questions.
Yes, thank you.
No problem.
So I have one question. In the conclusion, you mentioned that beyond visualization of metrics, data can be explored with other data science techniques. Could you comment on what kind of tools and what kind of work can be further be done with this data?
Yes. So basically, you can use any tool or framework that speaks SQL or PromQL and easily extract the data that is on our PromScale database. So if you knowing this, you basically have endless options. I can give you some examples. For example, you can apply machine learning techniques, which may allow you to find patterns in the data that can be helpful in the detection of non-efficient deployed jobs. Or also you can use machine learning to predict future use of compute node resources by a job. You can also apply even deeper data analysis that Grafana provides with PDF reports using Python libraries such as Pandas, Matplotlib, Seaborn, and others. And as a last example, you can use deep learning for decision making. For example, if a job is detected as faulty, it can be canceled out. I hope that answered your question.
Yes, thank you. Also, like another question is the architecture that is shown adaptable to work in other scenarios? And do you have any examples for that?
Yes, definitely. You can not only you can use architecture as it is for other scenarios, but you can also change the components of the system to better adapt to your necessities. For example, if you do not require SQL at all, you can just easily swap the database for Victoria metrics. Or if you require metrics to be pulled from targets, you can also configure that in VM agent. You have a lot of flexibility in this architecture. Any scenario that requires monitoring and that uses Prometheus-based metrics can easily have this architecture implemented without too much hassle. It does not have to be an HPC scenario.
Okay, thanks a lot.
No problem.
I guess we can wait like a minute or two for any other questions before we conclude the session. Okay, so if we don't have more questions, we can go ahead and conclude this session with, could I share my screen now? Julia?
Yes, sorry, of course.
Thanks. Okay, I hope my screen is visible. Right. So thank you for everyone for your participation and for questions. I think it's time now to close this webinar. Please stay tuned for the next webinar, which will take place on January 26th, 2023, by Samuel Bernardo from LIB, who will talk about BigHPC platform delivery into HPC clusters. Thank you again for joining us, and we can conclude the webinar now.